An important step in DNA barcoding is to try to identify the species or its closest relative associated that's associated with the cytochrome C oxidase fragment that was extracted and sequenced from your specimen. And so a simple way to do this is to perform what's called a sequence similarity search against a protein sequence database, and this search will identify matches to the sequences within your data set. And the perfect program for this process is called BLAST, and one of the versions of BLAST that we'll be using is called BLAST-X. It's very popular. It's called pairwise local alignment search tool, and it will compare the amino acid sequence translations of a DNA query sequence to a protein sequence database. And so from this search, any significant matches that are found by BLAST-X will be retrieved and sorted in a list based on the significance of that match, or based on the significance of that alignment. So what we're going to do is we're going to take our contigs and blast them against the protein sequence database containing thousands of sequences of cytochrome C oxidase. So if you've assembled all your data, then go ahead and use that data. If not, you can go ahead and use mine. If you go to my website, you can download the third zip file to the desktop. So collection of assembled forward and reverse reads. So if I go to my desktop, I can double click on this file, and then I can get access to all of the sequences. And so also on my website there is a link to BLAST. If you go ahead and click on the BLAST link, which is here, we can open that in a new tab, and then of the flavors of BLAST, as you can see, I've already used BLAST-X. Go ahead and click on BLAST-X. This is what the input page looks like. Here you copy in your sequence, and here you change your genetic code. For example, because we're looking at bugs, we want to use, or we're going to want to use the genetic code for invertebrate mitochondria. And then here's the BLAST button to go ahead and execute. This is the database, the default database that we will be searching. So one way to do this exercise is to copy and paste individual sequences into this search box, and then to run the BLAST button, and you can repeatedly do this. An easier way is to go ahead and copy all of the sequences into this box and allow BLAST to go ahead and perform the searches for each one of the sequences individually, and then we can look at the resulting, or the results. So in order to do that, first we need to create what's called a multi-FASTA file. So if I minimize this, here are all of our sequences. What I would like to do is concatenate all of these sequences into one file, creating a multi-sequence FASTA file. And the easy way to do this is to use BioEdit. So let's go ahead and open up BioEdit. We double click on it, and then click on New Alignment, and then go to File, Import, Sequence Alignment File. Then we have to navigate to where our folder is. We might have to extract those sequences first, because I don't think BioEdit will allow me to open that zip file. So yes, so let's back up. I'll minimize this. I'll go ahead and extract this all the sequences from this file. So now when I go back to BioEdit, I can go to File, Import, Sequences from Alignment File, go to my desktop, and then go to Assembled Forward and Reverse Reads. Then click the drop box and select all files, and then I can go ahead and, so what I want to do is I'm going to import all these files at the same time. So in order to do this, I can hold down the control button and hit the A. Oh nope, that doesn't work. I will just hold the shift button down, select the first item, and then hold the shift button down and press on the second item. That highlights the top all the way down to the bottom. Then I can click open. All of the sequences are now imported into the alignment file. So lastly, all I want to do now is just save this file or export this file. So if we go to File, go to Save As, and then type in, for example, contigs multi-fast A. Okay, and let's save this to the desktop. Click Save. Now we can close BioEdit because we're done with BioEdit. And here we find our file in on our desktop. Now let's open this in a simple text editor. For example, I like WordPad. And here are our sequences in what's called a multi-sequence FASTA file. So now I simply want to copy these and paste these into the BLAST window. A shortcut is to hold down the Control button and hit the letter A, highlights everything, then Control C for copy. Now I can go back to my browser, and now I can click into the input box. I can hit Control V to paste all my sequences in, and then I want to change the genetic code to invertebrate mitochondria, and then click BLAST. So once the search is complete, you'll see the BLAST-X results for the first sequence in our multi-sequence FASTA file, from our multi-sequence FASTA file. In the drop box labeled Results For, here at the top, you can use this to maneuver through the other sequences within our multi-sequence FASTA file. Here's a Mara House, here's Bold Jumper, here's Gold Weaver, something called Caddy E, so forth and so on. So the first graphic summary with all the red lines simply gives you a global view of how the sequences pulled from the protein sequence database extend along the length of our query sequence here. And the red color, of course, correlates or corresponds to the associated alignment score that this sequence achieved with our query sequence. Below the graphic summary, you'll find the descriptions. This provides a list of the sequences that align the best to the translations of our DNA sequence. This is a sort of list based on the e-value, and so this e-value is a statistical measure of significance. The lower the e-value, the lower the likelihood that this alignment will be observed between two unrelated sequences while searching this database. So for example, here's the first sequence. The maximum alignment score is 366. It covered 99% of our query sequence, and the percent identity is 98%. So if we wanted to observe the details of this first alignment, we can left mouse click on the first item in our list, and then this will take us to the details of our pairwise local alignment. The algorithm's goal is to position the characters in such a way between both sequences that maximizes what are called identical matches in the vertical columns, and to minimize mismatches and gaps within the vertical columns. And if we observe this alignment here, we can see that in the middle will highlight whether or not the match is an identical match by representing the character in the middle line, or if it is a mismatch, you'll either see a gap here, an empty space, or you may see a plus sign. So what is the difference between an empty space and a plus sign? Well, amino acids can be grouped together based on their physical chemical properties. Some amino acids may be basic, some are acidic, some are hydrophobic, some are hydrophilic, and oftentimes you can substitute, for example, an acidic amino acid or one amino acid for another that has a similar physical chemical properties. So for example, a leucine being substituted for a valine is considered to be a similar substitution or a conservative substitution. A methionine to an isoleucine is also considered to be a conservative substitution. In this alignment, we actually don't see any gaps. However, if there were gaps in this alignment, that gap would represent an insertion or deletion event. And so from an evolutionary perspective, what this means is that since these two sequences shared a common ancestor, there was a change that occurred. In the instance of a substitution, either this bottom sequence incurred a substitution to a valine, or maybe the query sequence incurred a substitution into a leucine. So the reason for performing this sequence similarity search is not to identify evolutionarily related sequences. our purpose is to try to identify the identity of the sequence or the organism from which this sequence was extracted. And so if we assume that the sequence that we submitted is supposed to be exactly like or is supposed to be exactly like the sequence from this organism, then how do we then interpret these differences between our sequences? So in order for one amino acid to change to another amino acid, there must have been a mutation at the DNA sequence level. How do we interpret that? Is that a true polymorphism that exists within that population or within this population of this organism? Or could it be an error within our sequencing? Did we not clean our data well enough such that we didn't eliminate enough of the bad base calls? That's something that we can't answer at this point in time. The only thing we can do is we can highlight these differences that are in the between our query sequence and the subject sequence and just make note of that. An additional thing I'd like to highlight are some of the scores here. This here, -3, tells us that the DNA sequence was translated using the reverse complement of the query sequence that we provided it by giving it the negative sign. And then starting with there were 0 gaps in our alignment, 221 positives. And what this is the total number of identical matches and the conservative substitutions, those 2 plus signs there. Here's the expectation value and the alignment score. So now what we would like to do is we would like to take this annotation and add it to our multi-sequence FASTA file. So in order to do that, we can click on this link here. This is called an accession number. It's a unique identifier for the database file from which the subject sequence was extracted. Let's go ahead and open this in a new tab. And this is what a database file will look like for this sequence. It's a lot of information here. But what we want to do is we want to add an annotation to our FASTA file. In essence, we want to add to it the name of the sequence and the organism name. An easy way to do this is to go ahead and click on FASTA link, the FASTA link here at the top. And this will then transform that huge database file into a smaller FASTA file. And then what we can do is then we can copy this line. This will not give us a large carriage return. We can copy it, minimize it, scroll up to the top of our file, and then just paste it into our multi-FASTA file. And we want to continue doing that with the rest of the sequences within our multi-sequence FASTA file. So we'll go back to the browser, and here's my tab where I have my BLAST search results. I'll scroll all the way back to the top, and I'll go to the second sequence in the BLAST results. Everything changes. The graphic summary changes, the descriptions change. We can click on that link to observe the details of the pairwise local alignment. And here we have some more non-conservative substitutions and some conservative substitutions here. Here we see that it's actually in the first frame, and beginning with that first nucleotide, that would be the frame from which the amino acid sequence was extracted or translated. We can click on the accession number. It opens in a new tab. We can click on FASTA, and then we can then copy and paste the information. And so don't copy in the greater than sign, just copy in everything after the greater than sign. Alt tab will take us back to our multi-sequence FASTA file. We can copy and paste that in. And so you want to continue doing this for the other 5 sequences within this list.